IME 312. Summer Online Course. Data Management and System Design. Industrial and Manufacturing Engineering Department. College of Engineering. Cal Poly State University. San Luis Obispo. Database models include hierarchical, network and relational. Combined, the first two are called pre-relational, also known as legacy database models. We are focusing on the third one, which is relational, in this course. What is a database system anyway? It is a combination of software and hardware that makes it possible and convenient to perform one or more tasks that involve handling large amounts of information. Then, what is DBMS? We have seen often on the publishing. It is a general-purpose software used for constructing particular database systems. The desktop Microsoft Access software is a typical example of DBMS. Others you may have heard are Oracle 9, IBM DB2, MySQL, SQL Server, DBase or Sybase. Let's first understand why relational database model is better than legacy DB models. We use DOS prompt to explain hierarchical. Hierarchical is also called a tree structure if you flip it upside down and imagine the root is in the ground. The tree structure is very rigid because if you store the file in a node which you don't remember, it will take a long time to search it out. See how repeated operations on DOS to enter the right branch to locate the desired file. Under the C prompt we type in CD to change to a lower hierarchical level. By issuing dir can display the content within the subdirectory. Using CD ... to move back to where the pointer is coming from. Again, use CD to move into another subdirectory. Hence, if we don't know where the file is stored in, it will be difficult to locate. Another example we can exemplify hierarchical is to use the old library card-based lookup system to locate a book. Do you still have any recollection on the old cards system? The card-based system requires us provide either title of the book, name of the author, or subject in order to locate the inventory card. The three categories have three different cabinet areas to search on. The library merely duplicates the same inventory card and places into these categories to improve successful found rates. In fact, adding indexes to enhance search capability here, it is similar to what a network model is achieved. Do you see any disadvantage of the hierarchical model? Yes. If one misplaced a card, then that book could never be found due to all cards are arranged alphabetically from front to back. Okay, now let's use an academic environment to explore more. Assuming that you have been accepted by Cal Poly and is now reporting to the administration to register officially, the staff gives you a card to fill in. See image on the background. After turning in, you went home, and found that you have misread the contact number of your landlord and placed the wrong one on the card, so you returned to campus for correction. Now you have arrived at the administration again. The staff upon your request goes to the pile which has already been organized alphabetically to pull out your card. You correct it and hand it back. The staff must put it back to where it was pulled out, otherwise next time when you ask for another update the card won't be found. Can the system be improved? How about design a bunch of holes around the four edges of the card? Let the holes be grouped by special service functions. For example, the top two holes are designating college. If we punch only the first hole and leave out the second hole, the result is a representative of College of Science. When both holes are not punched, it represents engineering. The other two colleges are defined similarly. As a result, we use the first two holes to symbolize four different colleges. With continuing 5 holes, we can symbolize 32 different binary combinations, therefore can comprise 26 A through Z characters for initials of the last name. How does it work with the new design? Under a new hypothetical scenario that you return administration for phone number correction. In order to search out your registration card, the staff asks you which college do you belong to. You say engineering. The staff uses 2 solid rods, similar to the knitting needles your mom or grandmother has been using, and attempting to go through the 2 holes on top edge of the card. Probing on the first hole on the card one by one in sequence, if there is a punched hole the rod can pick up, the card will stay on the rod, otherwise the card will be dropped. Eventually, when all cards have been processed, we obtain 2 groups, one is cards attached to the rod and the other all dropped cards. Can you tell that engineering and business students are not being picked by the rod? Those students belong to science and architecture are on the rod in terms of cards. After collecting all dropped off cards, the next step is to utilize the second hole on top of the card to filter further which card is of engineering student and which is not. Again, we probe through all cards and pick up all second hole available candidates. Repeated with similar filtering, search, procedure via last name, and major, sooner or later, your card is surfaced and handed over to you for phone number correction. Question: after you complete the phone number correction, does the staff must place the card back to exactly where it was found in the stack? Apparently not. As long as the card is in the pool, we can dichotomize the pool again and again based on selection criteria, and eventually the target card or cards will be found. In mathematical term we call the beginning and resulting pools set. See image how when both punched holes are sought architecture is separated from others. Further down, filtering the remaining cards on the first hole, we obtain science. The leftover contains business and engineering. The new design evinces that a card can be placed anywhere in the data pool and can be searched out through proper methodologies. Here the data pool can be expanded to big data concept and the methodologies to queries, data mining algorithms or artificial intelligence data science explorations. On the right we are observing what MIS access is used in constructing a query to scoop or sieve against a data pool. With repeated scooping or sieving actions, sooner or later matched data sets from data pool will be identified and reported. Once again we invent a digital environment to cross-check the registration search a card scenario. This is a data pool stored in Microsoft Access's table called registration. We designed 7 holes to store basic student information. The first 2 are indicating college and the remaining holes for last name. In the cell we use 1 to represent the hole is punched and 0 for intact. Now each row we see in the table is equivalent to a card in earlier physical environment. How to search out College of Engineering students like you. We'll need to construct a query and run it against the registration table. Details of construction will be taught later. Running the query. Type in 0 for hole 1 and also for hole 2 because we want to search out engineering students. As the execution result, we see the cards have been identified. Thus a change can be made accordingly if other data fields exist, such as the contact phone number. Summarizing. In relational database, when the records, cards, are organized in a table records set, the sequence order in the table does not matter. One may insert a row, records at any position and take out, delete, any record at any position. Relational DBMS laying out data storage in two-dimensional area where row and columns are constructed. Row is also called records or tuple, column is field or attribute. Query is to inquire about what has been stored in the tables. You may have heard of SQL, which is a query language working with relational DBMS. We'll talk about it more later.